Welcome back. Today we're going to start our fourth unit of the year. Coincides with Chapter 7 and it relates to exponential and logarithmic functions. Today's goals for Section 7.1 and 7.2 will be as follows. Be able to graph exponential growth and decay functions. Be able to use exponential growth models to predict how much money will be in a bank account given an interest rate and period of time. Use exponential decay models to calculate how much an object, such as a car, will depreciate or lose value over a given period of time. Have these down, and we will be looking at various aspects of growth and decay functions in the following notes. Okay, so what are exponential growth and what are exponential decay models? The models look very similar. They're going to be able to form y equals b to the x for both growth and decay. And obviously we may have a value in front of b at times, but what is the main point of this? Well, if it's growth, your b value is greater than 1. Okay? If it's decay, your b value is between 0 and 1. Okay? The graphs basically look like this. Growth, it's going to be getting larger as we go to the right. Notice it's a gentle curve. It's not a U curve necessarily, but it's a sloping curve. And decay will look something like this. It looks like a plane landing on the right, a plane taking off on the left, because we read their graphs left to right. So keep that in mind. Growth on the left, decay on the right. Forced in a pair function. Right now, these graphs have an asymptote of y equals 0. Remember, asymptotes like those imaginary lines, the graph will not cross. Now, when we add or subtract stuff outside of the b to the x, that's going to move our graph up and down, and it's going to move our y asymptote y equals 0 up and down. So that k value, if you will, that we're going to add and subtract outside of b to the x is going to manipulate our asymptote line and change that as well. So keep that in mind as we proceed through the chapter. Okay, let's look at exponential growth functions. Remember the parent function f of x equals b to the x, where b is greater than 1. Here's an example. F of x equals 3 to the x. It's a very generic exponential growth function. In this case, our b value is 3. Okay, so it is growth. When we're graphing these, some things I'm going to ask you to look for, okay, are the domain, the range, growth or decay, the asymptote line, and then 3 points on the graph. Okay? Well, let's look at the domain. Is there any values for this function that we can't plug in for x? For instance, is there anything where we plug in an x, is our domain going to be undefined? The answer to that one is no. I can plug in positive or negative real numbers for x, and I will get outputs. So my domain is going to be all real numbers. And that should hold true for all exponential growth equations. Okay? So the range is where it's going to be different. The range, you're going to have to use a combination of what's being added or subtracted outside of b to the x, and whether the graph is above or below the asymptote line. So if we look over here, there's nothing being added. It's just 3 to the x. There's no plus or minus anything outside. So we start with an asymptote line of y equals 0. So our asymptote is y equals 0. So we have that fact. We can now go to the range, and we're going to say all real numbers, or all y, such that are they larger or smaller than 0? Well, look at the graph. Our y values, they're all above the x-axis. If they're above the asymptote line, then it's greater than. It will never be greater than or equal to, because remember, if there's an asymptote line, the graph gets really close but doesn't touch. In our graph, it looks like it's touching, but if you zoomed in and went far to the left, there would also always be a gap between the graph and the x-axis. It never really touches it. Okay? And to get our 3 points for our graph, I would just go to y equals, like I did to graph this one, 3 to the x, go to the table, and we're going to pull our table out. And we're just going to graph 3 points. Okay? So 0, 1, That's on the graph. And 1, 3 over 1 up 3 is on the graph. And 2, 9 is on the graph, which is way up here. Okay, and there is our graph. So that's all I want you to do, or you can make your table on your own, but just so you get 3 points so you get the general curve of the graph. Okay? Is there anything else that we need? We got the asymptote. Oh, is it growth or decay? Well, that should be pretty evident. It's getting larger. The x and y values get larger as we move to the right. So this is an exponential growth. You probably should answer that one right off the bat, but that's okay. This is a growth model. So we've answered all the questions for that one. Let's look at another example. Okay, here's another example. If we look at this one here on the right, it says f of x equals 1/2 to the x. Notice our b values between 0 and 1. We look at the graph, and we graph it on our calculator. It's sloping down as we go from left to right. So is this a growth or a decay function? This is a decay function. Okay, we're looking for the asymptote line. Our asymptote, once again, our asymptote line, well, do we move it up or down? Is there anything being added or subtracted outside of 1/2 to the x? There's not. So asymptote is y equals 0. Our domain, there's still no limit on what we can plug in, so it's still all real numbers. And then our range. Our range, if we look, are values above or below the asymptote line. Here's the asymptote line, y equals 0. Even though it's decreasing, it's a decay, all the values are still above that line. So our range is all y greater than 0. Okay, we got our values that we can plot in. We need 3 more points to graph. I can pick any 3 I want. -3, 1, 2, 3, up to 8. -2 up to 4. 2, 3, 4. And 0, 1. How about that? There's 3 points. We made our curve. Okay, those are just easier to graph than the decimal, but you could use the decimals 1.5, 2, 0.25, etc. So there's some examples of growth and decay. Okay, so now let's get into more complicated looking models. Now this is a more standard form of exponential growth and decay models. A times b to the x minus h plus k. Once again, that h and k are in here again. The thing that separates decay and growth is the b values. Again, b is greater than 1, it's growth. If it's between 0 and 1, it's decay, just like the last equations we had. So what does h do? Well, h is going to be our left and right, like it was in previous units. It's a left and right movement, and k is up and down. And that's true for both of these functions, both growth and decay. H is left and right, k is up and down. Okay, remember it's whatever makes x minus h equals 0. So if I have x plus 3, then really we're moving 3 units left, because h would be a -3. Just keep that in mind. So when we're looking at this, what's our domain and our range going to be for these in general? Okay, well in general, our domain is still going to be all reals. Okay, our domain is all real numbers. And that's going to be for both. Our range, it's either going to be y is greater than k or y is less than k, depending upon whether the values are above or below the asymptote. Same thing over here. Okay. Growth and decay, it's going to be growth in this case if b is above 1. If b is between 0 and 1, it's decay over here. Our asymptotes are y equals k for both. And then we're still going to get 3 points from the table. Okay? Just 3 points is just enough points to graph it and get the shape. So that's kind of the characteristics of both growth and decay functions. Really, if you look through it, they're very similar. The only difference is b. B is going to tell us whether it's growth or decay. When you graph it, you're going to see whether it goes up or down. If it goes down from left to right, it's decay. If it goes up from left to right, it is growth. So general growth models, y equals a times 1 plus r to the t, and decay models, y equals a times 1 minus r to the t. Here's an example of something we'll wrote. This is from page 43, number 30 in your textbook. You purchase an antique table for $450. The value of the table increases by 6% each year. How much is the table worth in 3 years? This is a case of appreciation. Appreciation is when something gets larger, when you make money on it every year. So an investment appreciates. That's what you want. If you buy something, you want it to appreciate it. You want it to get more money. Unfortunately, not all things work out that way, as we'll see in the next example. But in this case, you bought an antique table. It grows 6% each year. How much is it worth in 3 years? Well, we can use this model. Y equals a times 1 plus r to the t. A equals the initial amount, or starting amount. R equals the rate of growth, or decay. Same thing for both. And T is time. So, in this case, our A, $450, our rate is 6%, our time is 3 years. We plug it in. There's only one thing you got to be wary of, and that's the rate. When you plug that in, we don't plug in 6. We need to change 6% to a decimal. That's 6 divided by 100, or 0.06. So be wary of that when you're plugging these into these formulas. So now in our calculator, we can just plug that in. 450 times 1. You may not need the calculator to do the 1 minus 0.06. 0.94. Excuse me, 1 plus. We're appreciating, right? Not depreciating yet. And the time is 3 years. Put 3 up here as a power. Plug it in. We get $535, and we'll call it 96 cents. Okay? So your table in 3 years is going to be worth $535.96, rounding it to the nearest penny. Okay? How about a decay function? You purchase a bike, a new mountain bike for $200. The bike decreases in value it depreciates by 25% per year. Why might it depreciate per year? You might think about that. Well, just like with cars, you're going to put wear and tear on it, and it's going to break down. It's going to need to get fixed, so it loses value. When you buy a car, it's not an investment. It's just something you use. Same thing with the bike. When people go to sell it used, it's usually less than what you paid for it. Once you have a classic car or a classic bike, I suppose you could be that case as well. So if we want to know what it's going to be worth in 3 years, we use the depreciation model. Y equals a times 1 minus r to the t. A, r, and t are the same thing they were in the last example. Okay, so we're going to use y equals 200. That's how much we paid for the bike. It's depreciating by 25%. That's 0.25 in this time 3 years as well. We plug this into our calculator. 200 times 1 minus 0.25. And then to the third column. In other words, it's 75% of what it was the year before, every year, and eventually, after 3 years, our mountain bike that cost us $200 is only worth $84, and I'll give you the penny, 38 cents. Okay, so those are situations where things appreciate and things depreciate with the basic interest formula. Okay, last one, this is a compound interest formula. This is the formula your bank will use to calculate how much money you make in your account when you deposit money into a savings account, for instance. They'll use something like this. How often they compound it, that's what's going to change, but this is the general model. A equals P times 1 plus R divided by N, the N times T. A is the final amount in this one. P is the principal, not your principal, not Mr. Ingham, but principal. That's what you're starting with, the initial amount. Okay. T is years. R is the rate, just like we did before. And N is the number of times it's compounded per year. Okay. So sometimes a bank will compound quarterly. That's 4 times a year. Sometimes they'll do it biannually, that's twice a year. Sometimes it's monthly. It just depends on what the agreement is on the loan or on the savings account interest. So you deposit $3,000 in an account that pays 4% annual interest. That's a good investment these days. Find the balance after 3 years if the interest is compounded quarterly. Quarterly means 4 times a year. Okay, so keep that in mind. So we're going to use that when we see it so many times per year. We know it's going to be this new compound interest formula, R over N times N to the T. So if you look, our principal amount, that's P, that's $3,000. Our rate is 4%. 4% is 0.04, the decimal, 4 divided by 100. And it's compounded quarterly. That's 4 times a year. That's what N is. To the 3 years times 4. So we can plug this in our calculator. And it's up to you whether you want to do it in chunks. Okay, but you can put it all in at once. I'm going to show you how. Alpha y equals, we can do a fraction, 0.04 divided by 4. All to the power of 4 times 3. 1 is 12. And we get, oops, what did I mess up on? I forgot to put 3,000. I put just 300. We didn't lose money on it. That'd be a bad investment. Okay, so. Let's insert a 0. And let's try it again. That's better. $3,380.48. So at the end of time frame, 3 years, we'll have gained $380.48 just by letting your money sit in the bank. Interest rates generally aren't that high right now. I don't know when this problem was written, but generally nowadays the interest rates are much, much lower, like 1% or less. So, but this is what it would be if it was 4%. So hopefully you have that. So hopefully we realize we hit our targets here today. We graphed growth and decay functions, and we use exponential growth and exponential decay models to find the appreciation, depreciation of value over a period of time. Depreciate, I didn't write it down on that slide back there. That's the opposite of appreciate. If it depreciates, it's going down in cost. That's like the bike example where it was losing value every year. A car would also generally be in that situation. So hopefully you have your notes down. We'll be checking them tomorrow. Have a wonderful day.